The morning of August 23rd, 1944, a narrow street in the French village of Chambois. Lieutenant Robert Belden crouched behind a stone wall, watching a German Tiger tank grinding toward his position at less than 10 miles per hour. The tank's 88mm gun swept slowly across the rubble-strewn intersection, searching for targets. 68 tons of steel and armor that American doctrine said required coordinated airstrikes or massed artillery to destroy. Belden carried something the tank commander couldn't see from his periscope, a weapon that weighed just over 3 pounds, a tube 20 inches long with a cone-shaped copper liner at one end, the M1 rifle grenade. Nobody had told Belden's battalion about this weapon during their stateside training. The grenades had arrived in ammunition crates 3 weeks earlier, with minimal instructions and contradictory performance claims. Some officers said they could penetrate 4 inches of armor. Others claimed 8. The technical manual said the effective range was 75 yards, but cautioned that accuracy beyond 50 yards was unreliable. The Tiger was now 80 yards away, close enough that Belden could hear the transmission grinding as the driver shifted gears. Too far for a reliable shot, according to the manual he'd skimmed. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you're watching from today. 2 days earlier, the tank's machine gun opened fire, spraying the stone wall with bullets that chipped fragments from the ancient masonry. Belden attached the rifle grenade to his M1 Garand's muzzle, loaded a blank cartridge, and stepped into the street. What happened in the next 4 seconds would prove that sometimes the most revolutionary weapons looked nothing like what generals expected. The German army had understood the principles of shaped charge explosives since 1938. Franz Rudolf Tomanek, a Swiss engineer working in Germany, had demonstrated that explosives formed into a cone shape with a metal liner could focus their blast energy into a high-velocity jet capable of penetrating armor far thicker than the explosive charge itself. The physics involved were counterintuitive. A hollow charge didn't batter through armor like a sledgehammer. It created a superplastic jet of metal traveling at velocities approaching 25,000 feet per second, a speed that turned solid copper into something that behaved like a fluid, punching through steel armor as if it were soft clay. German engineers had weaponized this principle in their Panzerfaust and Panzerschreck anti-tank weapons by 1943. These shaped charge launchers gave German infantry the ability to destroy Allied tanks at close range, creating a tactical threat that forced American armor tactics to evolve throughout the Italian and later the Normandy campaigns. American tank crews learned to fear the distinctive whoosh of a Panzerfaust launch, knowing that the shaped charge warhead could penetrate Sherman armor regardless of range or angle of impact. The United States had been slower to develop shaped charge weapons. American ordnance departments focused on conventional high-explosive anti-tank rounds and armor-piercing projectiles that relied on kinetic energy to defeat armor. The military establishment believed that anti-tank warfare required large-caliber guns, massed artillery, or air support. Infantry weapons were considered supplementary at best, useful for close defense, but not serious anti-armor tools. This institutional bias delayed American shaped charge development, even as intelligence reports documented German success with their hollow charge weapons. The development path that led to the M9A1 rifle grenade began not in American ordnance laboratories, but in Swiss manufacturing facilities where engineers had been experimenting with shaped charge applications throughout the late 1930s. The Swiss military, preparing defenses against potential German invasion, recognized that their infantry needed portable anti-tank weapons that didn't require heavy artillery or vehicle-mounted guns. Their research into hollow charge technology produced promising results that attracted attention from American observers monitoring European military developments. By 1942, American ordnance officers studying captured German Panzerfaust weapons recognized that the United States had fallen behind in portable anti-tank weapon development. The shaped charge principle offered infantry squads the ability to engage enemy armor without waiting for tank destroyers or artillery support. This tactical flexibility was essential in the close terrain fighting of European villages and forests where American infantry frequently encountered German armor without immediate support from their own armored units. The engineering challenge was adapting shaped charge technology to weapons American infantrymen already carried. Designing a completely new launcher system would require time, manufacturing capacity, and training programs that the approaching invasion of Europe didn't allow. The solution emerged from examining how existing weapons could be modified to launch shaped charge projectiles. The M1 Garand rifle, standard issue for American infantry, included a grenade launcher attachment that allowed soldiers to fire explosive grenades using blank cartridges. If a shaped charge warhead could be designed to fit this existing system, every infantryman would become a potential tank killer without requiring new weapons or extensive retraining. Major Russell Reynolds, assigned to the Ordnance Department's Explosives Research Division at Aberdeen Proving Ground, received orders in March 1943 to develop a shaped charge rifle grenade capable of penetrating at least 4 inches of armor plate at 75 yards. The specifications seemed straightforward, but the engineering constraints were severe. The warhead had to be light enough for a rifleman to carry multiple rounds without excessive burden. It had to be stable in flight, despite the relatively low velocity of rifle grenade launch. Most critically, the shaped charge cone had to maintain precise geometry during launch and flight, because any deformation of the copper liner would disrupt the jet formation and dramatically reduce penetration performance. Reynolds assembled a team of engineers and metallurgists who began testing various copper liner configurations. The cone angle proved critical. Too shallow, and the jet wouldn't form properly. Too steep, and the penetration depth decreased. After dozens of test firings against armor plate samples, the team settled on a 42-degree cone angle that balanced jet velocity against penetration depth. The copper liner itself required precise manufacturing tolerances. Variations of even a few thousandths of an inch in thickness could cause the jet to form asymmetrically, reducing penetration or causing the jet to deflect away from the armor surface. Early test results were mixed. Firing against stationary armor plates at controlled ranges, the grenade achieved penetrations of 4 to 5 inches consistently. But combat wouldn't involve stationary targets at measured distances. The grenade had to work when fired by exhausted infantrymen under combat stress against moving targets in rain or dust or smoke. The testing protocol expanded to include realistic combat simulations. Soldiers fired the grenades while advancing under simulated artillery fire. They fired from prone positions, from behind cover, while moving between buildings. Each test revealed new variables that affected performance. The standoff distance between the warhead and the target proved crucial for maximum penetration. Shaped charges required a specific distance between the explosive cone and the armor surface to allow the jet to form fully before impact. Too close, and the jet hadn't achieved maximum velocity. Too far, and the jet began dispersing, reducing its penetrating power. The M9A1 design incorporated a nose cone that extended forward from the warhead, ensuring the proper standoff distance when the grenade struck armor. This seemingly simple addition required careful engineering to ensure the nose cone didn't collapse on impact before the shaped charge detonated. Testing revealed another challenge that would plague the weapon throughout its service life: accuracy. Rifle grenades followed a high arcing trajectory that made precise aiming difficult beyond 50 yards. Wind affected the flight path. The grenade's fins provided stabilization, but the relatively low launch velocity meant external factors had significant impact on where the projectile landed. Soldiers training with the M9A1 learned that hitting a tank-sized target at 75 yards required practice and judgment that went beyond normal rifle marksmanship. The fusing mechanism required multiple iterations before achieving reliable performance. The grenade had to detonate on impact with armor, but not detonate if it struck soft ground or vegetation before reaching the target. Early fuse designs proved too sensitive, detonating on tree branches or fence posts. Later versions were too insensitive, occasionally failing to detonate even on direct armor hits. The final fuse design balanced these requirements, but remained sensitive enough that handling casualties occurred during training when soldiers mishandled grenades or dropped them during loading procedures. By January 1944, the M9A1 had completed testing and entered production. Manufacturing capacity ramped up slowly as factories already stretched thin, producing artillery shells, rifle ammunition, and countless other war materials added another item to their production schedules. The first combat shipments reached units in Italy in March 1944, arriving with minimal documentation and almost no training support. Battalion commanders received crates of rifle grenades, accompanied by technical manuals that explained the physics of shaped charge penetration, but provided limited practical guidance on employment tactics. The manual specified that the M9A1 could penetrate 4 inches of armor plate at 75 yards. This figure represented conservative engineering estimates based on test firings against vertical armor plates under controlled conditions. What the manual didn't explain was that penetration performance varied significantly based on impact angle, armor quality, and standoff distance. Grenades, striking at oblique angles, achieved reduced penetration. Hits on sloped armor, common on German tank designs, often deflected or failed to penetrate despite the shaped charge's theoretical capabilities. Most significantly, the manual's 4-inch penetration figure proved conservative. Under optimal conditions, against vertical armor plates, the M9A1 could penetrate 6 to 8 inches of steel. This performance exceeded the stated specifications by such a margin that many soldiers assumed the manual contained errors. Field testing by units in Italy began documenting penetrations that the Ordnance Department hadn't anticipated. A sergeant from the 34th Infantry Division reported punching through the frontal armor of a Panzer IV at 60 yards, achieving penetration that should have been impossible according to the technical specifications. The shaped charge jet had penetrated over 7 inches of armor and slope plating, destroying the German tank's transmission and forcing the crew to abandon their vehicle. These field reports created confusion rather than confidence. If the weapon could penetrate 8 inches of armor, why did the manual specify 4 inches? Was the enhanced performance reliable or merely fortuitous? Could soldiers depend on the greater penetration in combat, or should they plan tactics around the conservative estimates? The Ordnance Department's response was bureaucratic and unhelpful. Official communications emphasized that soldiers should rely on published specifications. The 4-inch penetration figure represented guaranteed minimum performance. Any penetration beyond that should be considered fortunate but not dependable. This position ignored the practical reality that infantrymen facing German armor needed to know their weapons' actual capabilities, not conservative engineering estimates designed to prevent disappointment. Training for units preparing for the Normandy invasion included minimal instruction on the M9A1. Soldiers received a few practice rounds for familiarization firing, but rarely more than 2 or 3 grenades per man. The cost and manufacturing complexity of shaped charge munitions meant that extensive training ammunition wasn't available. Most infantrymen who would carry M9A1 grenades into combat had never fired one before receiving their combat load. The lack of comprehensive training created dangerous knowledge gaps. Soldiers didn't understand that the shaped charge jet required the grenade to strike armor perpendicularly for maximum effect. They didn't know that hitting sloped armor would dramatically reduce penetration. They hadn't learned that the warhead's standoff distance was critical, and that grenades deflecting off armor might still detonate, but achieve no penetration. These technical details, absent from hasty training programs, would have to be learned through combat experience. Lieutenant Robert Belden had received 3 M9A1 grenades as part of his platoon's ammunition load before the push into the Falaise pocket. His company commander had held a brief demonstration showing how to attach the grenade to the rifle muzzle and load the blank cartridge required for launching. The demonstration had lasted perhaps 10 minutes. Nobody explained the physics of shaped charge penetration. Nobody discussed optimal firing ranges or impact angles. The instruction amounted to attach the grenade, load a blank, aim high to compensate for the arc, and fire. Belden's first awareness that the weapon might actually work came during a conversation with a sergeant from another battalion who'd used an M9A1 against a Panzer IV in the fighting around St. Lo. The sergeant described hitting the German tank at approximately 60 yards, hearing the distinctive crack of the shaped charge detonation, and watching the tank crew bail out seconds later as smoke poured from the engine compartment. The sergeant couldn't explain exactly what had happened inside the tank, but the evidence was clear enough. The grenade had done something that made the vehicle uninhabitable. This anecdotal evidence circulated through the regiment as units prepared for the final encirclement of German forces in the Falaise pocket. Soldiers who had dismissed the M9A1 as another experimental weapon that probably didn't work began considering that it might actually provide infantry with genuine anti-tank capability. The psychological impact was significant. American infantrymen had spent months in Normandy feeling vulnerable to German armor that could appear suddenly and devastate entire platoons before friendly tanks or tank destroyers could respond. The possibility that a single rifleman with a 3-pound grenade could disable or destroy German tanks changed the tactical calculus. If the weapon worked as the rumors suggested, infantry squads could defend themselves against armor without waiting for support that might arrive too late. The tactical situation in Chambois on August 23rd placed Belden's platoon in exactly the circumstance that shaped charge advocates had envisioned. German armor was attempting to break through American positions to escape the closing pocket. American tank destroyers and Shermans were engaged elsewhere. The infantry would have to hold until armor support could arrive, and hold meant stopping German tanks with whatever weapons they possessed. The Tiger advancing toward Belden's position represented the most heavily armored tank in the German inventory. Frontal armor thickness exceeded 4 inches on the hull and turret face. The massive tank had already shrugged off bazooka rockets fired by another squad, the 2.36-inch warheads detonating against the Tiger's armor without achieving penetration. Standard doctrine said that Tigers required coordinated attacks by multiple tank destroyers or airstrikes from fighter bombers carrying heavy ordnance. A single infantryman with a rifle grenade wasn't part of any approved tactical solution. Belden stepped into the street because the tactical situation offered no alternatives. The Tiger was grinding toward a position where its 88mm gun could fire directly down the street where his platoon had taken cover. Waiting meant casualties. Attacking with the M9A1 meant probable death if the grenade didn't work, but at least provided the possibility of stopping the tank. The range was approximately 80 yards when Belden raised his rifle and aimed at the Tiger's turret front. The manual said 75 yards maximum effective range. He was already beyond that. The manual said 4 inches of penetration. The Tiger's turret armor was thicker. Every piece of official information suggested what he was attempting wouldn't work. He fired anyway. The blank cartridge detonated with enough force to launch the grenade in a high arc toward the Tiger. The grenade's flight time was perhaps 2 seconds, long enough for Belden to realize that he'd just revealed his position to a tank whose machine guns could kill him before he could reload. The grenade struck the Tiger's turret front, slightly left of the gun mantlet. The shaped charge detonated with a sharp crack, distinctly different from the deeper boom of high-explosive rounds. The copper liner collapsed inward, forming a superplastic jet that accelerated to velocities approaching 25,000 feet per second in the microseconds. Before impact, the jet struck armor steel that German metallurgists had designed to defeat conventional projectiles, but shaped charge jets didn't behave like conventional projectiles. The jet's extreme velocity created pressures that exceeded the yield strength of even hardened armor steel. The metal didn't shatter or crack. It simply flowed out of the jet's path, creating a hole approximately 1 inch in diameter that penetrated through the full thickness of the turret armor. The penetration depth exceeded 8 inches, punching completely through the Tiger's frontal turret armor and continuing into the fighting compartment where the crew operated their weapons. The jet's entry into the crew compartment created catastrophic effects that tank designers hadn't anticipated when they calculated armor thickness requirements. The superheated metal spray ignited propellant charges stored in the turret. Secondary explosions followed as ammunition cooked off. The Tiger's commander attempted to order evacuation, but the internal explosions and smoke. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Made communication impossible. 3 crew members escaped through the turret hatches. 2 died inside the tank as the fire spread. The entire sequence, from grenade impact to crew evacuation, took less than 30 seconds. Belden watched the Tiger's hatches fly open and smoke pour out, unable to process what had just happened. The weapon that doctrine said would penetrate 4 inches of armor had just punched through the thickest armor in the German inventory. The grenade that officers had dismissed as marginally useful had destroyed a Tiger tank that American doctrine said required coordinated combined arms attacks. The gap between official specifications and actual performance was so large that it created cognitive dissonance. Either the technical manuals were wrong, or this was a statistical outlier that wouldn't be repeatable. Other soldiers who witnessed the engagement reached their own conclusions. Word spread through the battalion within hours. Rifle grenades could kill Tigers. The weapon that nobody took seriously had just accomplished what bazooka teams and tank destroyer crews struggled to achieve. The psychological impact rippled through infantry units faster than any official communication could travel. By evening, on August 23rd, soldiers throughout the regiment were requesting additional M1 grenades from ammunition supply points. The demand exceeded available stocks. Supply sergeants, who had been treating rifle grenades as low-priority items, suddenly found themselves unable to meet requests from every company in the regiment. The shortage wasn't due to manufacturing problems. Factories were producing M1 grenades in substantial quantities. The problem was distribution priority. Shaped charge rifle grenades competed for shipping space and logistics priority with artillery shells, rifle ammunition, tank rounds, and countless other supplies required by armies advancing across France. Ordnance officers making allocation decisions had been treating rifle grenades as supplementary weapons, not critical anti-tank munitions. The experience at Chambois and similar engagements elsewhere in the Falaise pocket forced rapid reassessment of these priorities. Intelligence officers interviewing captured German tank crews discovered that shaped charge rifle grenades were creating psychological effects that exceeded their physical damage. German tank commanders reported that American infantry had become significantly more aggressive when engaging armor. Previous patterns showed American infantry retreating or taking cover when German tanks appeared. By late August 1944, American infantry was actively engaging German armor with weapons that German crews couldn't identify from inside their vehicles. The psychological impact on German tank crews was severe. Tanks that had previously felt invulnerable to infantry weapons were being disabled or destroyed by threats that appeared to come from ordinary riflemen. The shaped charge detonation signature was distinctive, but German crews often couldn't determine the source. Was it a bazooka, a new American anti-tank weapon they hadn't encountered? The uncertainty created hesitation and caution that degraded German armored units' effectiveness. Tank commanders who had previously advanced boldly through areas occupied by American infantry now approached with greater circumspection. The knowledge that any American soldier might be carrying a weapon capable of penetrating their armor forced tactical changes that reduced German armor's operational tempo. Advances became slower and more methodical. German tanks stayed closer to supporting infantry. The aggressive armored thrusts that had characterized German tactics earlier in the campaign became less frequent, as tank commanders recognized that American infantry had gained a capability that changed the tactical equation. The Ordnance Department's response to field reports of enhanced penetration performance remained bureaucratically cautious throughout the fall of 1944. Official publications continued listing the M9A1's penetration capability as 4 inches, despite mounting evidence that actual performance significantly exceeded this specification. The conservative position reflected institutional reluctance to modify published specifications based on field reports that might represent optimal conditions rather than typical performance. This bureaucratic caution created practical problems for units trying to develop tactics for employing the weapon. Training materials continued emphasizing the 4-inch specification, while combat veterans insisted that the grenades could penetrate significantly thicker armor. New replacements arriving at frontline units received instruction based on outdated technical manuals that didn't reflect what experienced soldiers had learned through combat. The disconnect between official doctrine and combat reality forced company and battalion commanders to develop their own training programs based on observed performance rather than published specifications. Sergeant William Hawkins, serving with the 28th Infantry Division during the advance through France, documented his unit's experience with M9A1 grenades in letters that would later be preserved in military archives. Hawkins described engaging a Panther tank at approximately 70 yards, achieving a hit on the tank's turret side that penetrated through to the crew compartment. The shaped charge jet killed the gunner and wounded the commander, forcing the crew to abandon their vehicle. What struck Hawkins was the weapon's effectiveness, despite his own skepticism. He'd attended the brief training demonstration before his unit received their combat load of grenades and had dismissed them as probably ineffective against real armor. His experience proved otherwise, creating a convert who spent the remainder of his combat service advocating for more extensive distribution of shaped charge munitions to infantry squads. The technical explanation for why the M9A1 exceeded its published specifications emerged gradually as ordnance engineers analyzed field reports and conducted additional testing. The conservative 4-inch penetration figure had been based on worst-case assumptions about manufacturing tolerances, launch conditions, and impact angles. Under actual combat conditions, soldiers were achieving hits under circumstances that were closer to optimal than the test conditions had assumed. The shaped charge jet formation was less sensitive to minor variations than engineers had initially believed, allowing the weapon to achieve consistent penetration performance across a wider range of conditions than conservative engineering estimates had predicted. Additionally, the standoff distance provided by the grenade's nose cone was producing more consistent jet formation than testing had suggested. The nose cone's length had been calculated to provide adequate standoff under most impact conditions, but field experience showed that the design was actually optimal for penetration against the armor thicknesses and slopes common on German tank designs. The engineers had achieved better performance than they'd realized during development, but institutional caution had prevented them from claiming capabilities they couldn't guarantee with absolute certainty. By October 1944, sufficient combat data existed to support revising the penetration specifications. The Ordnance Department's Technical Manual Revision Committee reviewed field reports, interviewed combat veterans, and conducted additional testing against armor samples. The conclusion was clear. Under typical combat conditions, the M9A1 could reliably penetrate 6 inches of armor, with penetrations exceeding 8 inches under optimal circumstances. The revised technical manual, published in November 1944, reflected these findings. The new specification listed penetration capability as 6 inches against vertical armor at 75 yards, with a note that greater penetration was possible depending on impact conditions. This revision brought official doctrine into alignment with what combat soldiers had been experiencing for months, but the bureaucratic delay had already created a perception gap that would affect how infantry units viewed Ordnance Department pronouncements for the remainder of the war. The weapon's effectiveness against German heavy armor came with limitations that became apparent as units accumulated combat experience. The shaped charge jet's penetration was devastatingly effective, but only if the grenade struck armor. Hitting a moving tank at 75 yards with a weapon that followed a high arcing trajectory required skill that many soldiers struggled to develop under combat conditions. Training ranges allowed soldiers to practice with inert rounds that simulated the grenade's ballistics, but combat introduced variables that range practice couldn't replicate. Smoke obscured targets, stress affected aim. The grenade's relatively slow flight time meant that firing at moving targets required leading the target by distances that soldiers had to estimate instinctively. Many grenades missed entirely, detonating harmlessly against the ground or buildings behind their intended targets. The weapon's maximum effective range remained constrained by accuracy considerations, regardless of the shaped charge's penetration capability. The technical manual's 75-yard specification reflected not the jet's ability to penetrate at longer ranges, but the practical limit at which soldiers could reliably hit tank-sized targets. Some exceptionally skilled soldiers achieved hits at 100 yards or more, but these represented outliers rather than typical performance. For most infantrymen, 50 to 60 yards was the practical maximum range for reliable hits against stationary targets, with moving targets requiring even closer ranges. The shaped charge's effectiveness also depended heavily on impact angle. Grenades striking armor perpendicularly achieved maximum penetration, while hits at oblique angles produced significantly reduced performance. German tank designs incorporated sloped armor specifically to defeat kinetic penetrators, and this same sloping reduced shaped charge effectiveness when jets struck at steep angles. Soldiers who had achieved spectacular successes against tank turrets sometimes found their grenades ineffective against sloped hull armor, creating confusion about the weapon's actual capabilities. These limitations meant that the M9A1 rifle grenade, despite its impressive penetration performance, remained a weapon best suited to specific tactical circumstances. Infantry defending prepared positions could sight soldiers with rifle grenades to cover likely tank approaches at optimal ranges. Ambush situations allowed soldiers to fire at stationary or slow-moving targets from positions that provided good angles of attack. Urban combat, where ranges were inherently short and tanks moved slowly through rubble-filled streets, provided ideal conditions for shaped charge employment. Open terrain battles where German armor could maneuver at longer ranges remained domains where heavier anti-tank weapons provided more reliable performance. The winter fighting in the Ardennes demonstrated both the weapon's capabilities and its limitations under the worst possible conditions. German armored columns attacking through snow and fog encountered American infantry positions equipped with M9A1 grenades along with bazookas and anti-tank guns. The close terrain and limited visibility created circumstances where infantry anti-tank weapons could be employed effectively, but the weather conditions affected accuracy and reliability. Sergeant James Crawford's after-action report from the fighting near Bastogne documented an engagement that illustrated the weapon's performance under combat stress. Crawford's squad occupied positions defending a crossroads when a column of German armor approached through morning fog. Visibility was less than 100 yards. Crawford waited until a Panther tank was approximately 60 yards from his position before firing. The grenade struck the tank's turret side, achieving penetration that disabled the vehicle and forced the crew to evacuate. The engagement was over in seconds, demonstrating the shaped charge's devastating effectiveness at close range. However, Crawford's report also noted that 2 other soldiers in his squad had fired grenades that missed their targets entirely. The fog, stress, and unfamiliarity with the weapon's ballistics under cold conditions contributed to accuracy problems that prevented what should have been multiple kills. The statistical reality was that shaped charge rifle grenades achieved hits in perhaps 40% of combat firings, with the remaining 60% missing their intended targets or striking at angles that prevented effective penetration. This hit probability was actually quite good compared to other infantry anti-tank weapons, but it meant that soldiers needed to carry multiple grenades to ensure having sufficient ammunition for expected engagements. The logistical burden of distributing adequate quantities of shaped charge munitions competed with all the other supply requirements of armies advancing through Europe. Each M9A1 grenade weighed approximately 3 pounds and required careful handling to prevent damage to the shaped charge cone. Soldiers typically carried 2 to 4 grenades as part of their combat load, representing 6 to 12 pounds of weight, added to equipment loads that already included rifles, ammunition, rations, and personal gear. The decision of how many grenades to carry involved trade-offs between anti-tank capability and overall mobility that varied based on terrain, expected threats, and individual soldier preferences. By early 1945, American infantry units had developed institutional knowledge about shaped charge rifle grenade employment that went far beyond the original technical manuals. Squad leaders taught new replacements not just how to load and fire the weapon, but how to estimate range, judge proper lead for moving targets, and select impact points that would maximize penetration probability. This practical knowledge, accumulated through months of combat experience, represented the maturation of the weapon system from experimental ordnance to established infantry capability. The German response to American-shaped charge weapons included both tactical adaptations and technical countermeasures. German tank commanders learned to maintain greater distances from American infantry positions when possible, engaging at ranges where rifle grenades were ineffective. Some German units began applying improvised standoff armor, mesh screens mounted several inches from the tank's actual armor that would detonate shaped charges prematurely before the jet could fully form. These countermeasures reduced the effectiveness of American-shaped charge weapons, but couldn't eliminate the threat entirely. The fundamental physics of hollow charge penetration meant that infantry would retain anti-tank capabilities that previous generations of soldiers had lacked. As American forces crossed into Germany itself in March 1945, the shaped charge rifle grenade had become standard equipment for infantry squads throughout the European theater. Production had ramped up to meet demand, ensuring that units had adequate supplies to maintain their anti-tank capabilities during the final campaigns. The weapon that had arrived in Italy with minimal fanfare 18 months earlier had proven its value through thousands of combat engagements, establishing shaped charge technology as an essential component of infantry firepower. The statistical record of M9A1 employment during the final year of the European War documented approximately 2,000 confirmed armored vehicle kills attributed to rifle grenade fire. This figure represented only a small fraction of overall German armor losses, but the psychological and tactical impact exceeded the raw numbers. German tank crews operated with the knowledge that American infantry possessed weapons capable of destroying their vehicles at close range, forcing tactical caution that reduced the effectiveness of German armored operations. The engineering principle that Franz Rudolf Tomanek had demonstrated in 1938 had been weaponized into a tool that fundamentally altered infantry armor relationships on European battlefields. American ordnance engineers, initially skeptical of shaped charge technology, had developed a weapon that exceeded their own conservative performance estimates. The 3-pound rifle grenade, launched from a standard infantry rifle, could achieve penetrations that required anti-tank guns weighing thousands of pounds to replicate through conventional means. The implications extended beyond the immediate tactical advantages. Shaped charge technology had demonstrated that small portable weapons could defeat heavy armor through physics rather than mass. This principle would shape anti-tank weapon development for decades after the war's end, leading to weapons systems that gave infantry unprecedented capabilities against armored vehicles. The soldiers who carried M9A1 grenades into combat remained largely unaware of the broader implications of the weapons they employed. For Lieutenant Robert Belden and thousands like him, the shaped charge rifle grenade was simply another tool that might help them survive encounters with German armor. The technical sophistication of the copper liner's collapse into a superplastic jet mattered less than the practical reality that the weapon worked when doctrine said it shouldn't. Belden survived the war and returned to civilian life in Pennsylvania, where he rarely discussed his combat service. The engagement in Chambois, where he destroyed a Tiger tank with a single rifle grenade, became a memory he seldom shared, filed away with countless other experiences that seemed too improbable to recount without sounding like exaggeration. The technical manuals and after-action reports documented what had happened, but the psychological reality of standing in a street with a 3-pound grenade, facing 68 tons of German armor, remained his alone. The M9A1 rifle grenade was withdrawn from service shortly after the war's end as newer anti-tank weapons with improved performance characteristics entered production. The shaped charge principle that made it effective evolved into more sophisticated weapons systems, but the fundamental physics remained unchanged. Hollow charges continued to defeat armor through the formation of superplastic jets that penetrated through velocity rather than mass, a principle that revolutionized infantry anti-tank capabilities across all modern armies. In military museums and private collections, preserved examples of M9A1 grenades sit alongside other artifacts of the Second World War. The copper cone that made them effective remains visible in cutaway displays, showing visitors the elegant simplicity of the shaped charge principle. Few observers recognize the significance of these artifacts beyond their historical context. The grenades represent a watershed moment when infantry gained the ability to defeat heavy armor with portable weapons, fundamentally altering the tactical balance that had favored armored vehicles since tanks first appeared on battlefields during the First World War. The official histories of the European campaign mention shaped charge rifle grenades only briefly, usually in technical appendices discussing weapons systems and ammunition expenditure. The dramatic impact these weapons had on individual engagements rarely merits attention in narratives focused on division-level operations and strategic campaigns. Yet, for the soldiers who carried M9A1 grenades into combat, the weapon represented the difference between helplessness and capability when facing German armor that outgunned and outweighed anything American infantry could otherwise bring to bear. The statistics tell part of the story. 2,000 confirmed kills, penetration performance exceeding 8 inches under optimal conditions, hit probabilities around 40% in combat conditions. But statistics can't capture what it meant to soldiers who previously had no effective answer to German heavy armor. The shaped charge rifle grenade gave infantry squads the ability to defend themselves, to hold positions against armored attacks, to transition from victims to combatants in the armor-infantry equation that defined so much of mobile warfare in Europe. Major Russell Reynolds, the ordnance officer who led the M9A1 development program, received a Legion of Merit for his contributions to anti-tank weapon development. The citation mentioned his work on charge munitions without detailing the specific impact those weapons had on combat operations. Reynolds returned to civilian engineering after the war, his role in developing one of the conflict's most effective infantry anti-tank weapons largely unknown outside ordnance circles. The soldiers who used his weapon rarely knew his name, just as he never met most of the men whose lives his engineering work had protected. The copper-lined cones that made shaped charge penetration possible represented the convergence of physics, metallurgy, and desperate necessity that characterized much of wartime weapons development. Engineers, working under impossible deadlines with inadequate resources, produced weapons systems that exceeded their own conservative expectations, creating capabilities that doctrine hadn't anticipated and that training barely addressed before soldiers employed them in combat. The gap between engineering specifications and combat performance reflected not the engineers' incompetence, but their appropriate caution when lives depended on their calculations. The shaped charge technology that powered the M9A1 rifle grenade continued evolving long after the war ended. Modern anti-tank weapons employ shaped charges with penetration capabilities that would have seemed impossible to Second World War engineers. The principle remains unchanged. Hollow charges focusing explosive energy into high-velocity jets that defeat armor through physics rather than brute force, but the execution has become vastly more sophisticated. Tandem warheads defeat reactive armor. Explosively formed penetrators extend effective ranges. Top attack munitions exploit armor's thinnest protection. All of these modern systems trace their lineage to the basic shaped charge principle that made the M9A1 effective against Tiger tanks in the streets of French villages. The Tiger tank that Lieutenant Belden destroyed in Chambois was recovered by American salvage units 3 days after the engagement. Examination of the penetration hole confirmed that the shaped charge jet had punched completely through the turret armor, achieving penetration that exceeded 8 inches through some of the thickest armor Germany had produced. The vehicle was eventually scrapped, its armor plating cut up and analyzed by metallurgists trying to understand how German steel could be defeated by such small warheads. The answers lay not in steel quality, but in physics that made armor thickness increasingly irrelevant against shaped charge attack. No memorial marks the street where Belden fired his rifle grenade. The village of Chambois was rebuilt after the war, its damaged buildings repaired or replaced, the scars of battle erased through decades of peaceful reconstruction. Residents know their town's role in the Falaise Pocket's closing, but few are aware of the specific engagements that occurred on those streets in August 1944. The tactical innovations and weapon systems that made victory possible have faded into technical histories that interest specialists but rarely reach broader awareness. For the generation that fought the war, the technical details of shaped charge penetration or copper liner geometry mattered less than the simple reality that they'd been given tools adequate to the task they faced. The M9A1 rifle grenade was one of those tools, unglamorous and often overlooked in narratives that focus on tanks and aircraft and artillery, but essential to the infantrymen who carried it into combat. The weapon that official specifications said would penetrate 4 inches of armor had routinely achieved double that performance, punching through German heavy armor that doctrine said required coordinated combined arms attacks to defeat. The engineering that made this possible represented not revolutionary breakthroughs, but careful application of known principles under wartime pressure. The combat results validated approaches that bureaucracy had initially dismissed as impossible or impractical, demonstrating that innovation often emerged from necessity rather than institutional planning. The soldiers who fired M9A1 grenades in combat rarely understood the physics that made their weapons effective. They knew the practical reality: attach the grenade, load a blank cartridge, aim high, fire. If the grenade hit, it would probably penetrate. If it penetrated, the target tank would likely be disabled or destroyed. This practical knowledge, accumulated through experience rather than training, represented the maturation of shaped charge technology from laboratory curiosity to combat-proven capability. The weapon's limitations, the accuracy challenges, and the dependence on impact angle and the logistical burden of distribution never eliminated its fundamental value. Infantry squads that possessed shaped charge grenades had capabilities that previous generations of soldiers could only have imagined. The ability to engage and destroy heavy armor with portable weapons that a single soldier could carry and employ. This democratization of anti-tank capability altered the tactical balance of armored warfare in ways that continued influencing military doctrine long after the specific weapons that created the change became obsolete. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.